Right now, 4 billion miles from where you are sitting, the temperature is minus 230 degrees Celsius. Sunlight there is nearly 2,000 times dimmer than a cloudy afternoon on Earth. If you stood on the surface of Pluto and looked up, the sun would no longer appear as a disk. It would be a sharp, brilliant point, still the brightest object in the sky, but no longer the commanding presence that warms your face and fills your field of view. It would look like a very bright star, stripped of its authority, and Pluto is not even close to the far edge of what lurks out there. Beyond Neptune, stretching across billions of miles of frozen vacuum, lies a region so vast, so cold, and so empty that it shatters the tidy picture most people carry of the solar system. Scientists call it the Kuiper Belt. What they found there is already rewriting the rules. If you enjoy journeys that make you rethink everything you thought you knew about our place in space, do me a favour and hit that like button and subscribe. It means more than you know. Now, get yourself comfortable. Let's begin. The solar system does not end at Neptune. It does not even come close to ending at Neptune. What lies beyond that final blue giant is so vast, so physically extreme, and so poorly represented in popular imagination that learning about it for the first time feels less like an update, and more like discovering you have been living in a house and never noticed an entire wing of rooms stretching off into the dark. Scientists call this region the Kuiper Belt, and what it reveals about the true structure of our cosmic neighbourhood changes everything you thought you understood about where we live. Start with the basics. The Kuiper Belt is a broad, donut-shaped zone of icy objects that begins near the orbit of Neptune, at roughly 30 astronomical units from the Sun, and extends outward to at least 50 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, approximately 93 million miles. So the inner edge of the Kuiper Belt sits about 2.8 billion miles from the Sun. The outer edge, at 50 astronomical units, lies roughly 4.6 billion miles away. Some scattered objects associated with the belt reach far beyond even that boundary, pushing into regions 70, 80, or even 100 astronomical units from the Sun. These are not small numbers adjusted for a diagram. These are distances so large they break every intuitive sense of scale a human being possesses. If you drove a car at highway speed toward the inner edge of the Kuiper Belt, you would need to maintain that speed continuously for over 5,000 years just to arrive. The outer edge would require another 2,000 years of driving beyond that, and you would be driving through a vacuum, in total darkness, with the sun shrinking behind you into a point of light no brighter than a distant star. But the raw mileage is not the real shock. The real shock is what the existence of the Kuiper Belt does to the proportions of the solar system you thought you knew. Think about the familiar part. Mercury orbits at roughly 1/3 of an astronomical unit from the Sun, Venus at about 7/10, Earth at 1, Mars at 1.5, Jupiter at 5.2, Saturn at 9.5, Uranus at just over 19, Neptune at 30. The entire stretch of planets, from Mercury to Neptune, covers about 30 astronomical units. That is the solar system you learned. The one with all the names, all the missions, all the photographs on magazine covers. Now look at the Kuiper Belt. Its main body alone spans from 30 to 50 astronomical units. That is 20 astronomical units of additional structure, 2/3 the width of the entire planetary zone, bolted onto the end of the solar system, in a region most people have never heard described in any detail. And if you include the scattered disk objects that are dynamically linked to the Kuiper Belt but orbit on more eccentric paths, the Sun's icy outer debris field stretches to 100 astronomical units or more. That means the icy outer zone is at least as wide as the entire planetary system, and possibly far wider. The solar system, you know, the one with the rocky planets and the gas giants and the beautiful rings of Saturn, fits inside the inner third of the Sun's actual domain. Everything beyond Neptune is larger in radial extent. and almost nobody talks about it. This is not a recent discovery hidden in obscure journals. The Kuiper Belt has been a confirmed part of solar system science for over 3 decades. But getting to that confirmation required one of the most painstaking observational campaigns in the history of planetary astronomy. The idea of a belt of icy bodies in the outer solar system traces back to the 1950s. In 1951, astronomer Gerard Kuiper proposed that a disk of material might have existed beyond Neptune early in the solar system's history, though he suggested it had since been scattered away. Around the same time, Irish astronomer Kenneth Edgeworth independently speculated about a reservoir of small icy bodies in that same region. The zone is sometimes called the Edgeworth-Kuiper Belt, in recognition of both contributions, but speculation is not the same as detection. For 40 years, no one could confirm whether anything actually occupied that distant space. Pluto, discovered in 1930, was the only known object beyond Neptune. It was classified as the 9th planet and treated as a lone outpost at the edge of the solar system. The idea that it might be one member of a much larger population was considered plausible but unproven. Telescopes at the time simply could not detect the faint, slow-moving objects that populate the outer solar system. Kuiper Belt objects reflect very little sunlight. They are small, dark, and unimaginably far away. Even a body several hundred kilometers across appears as nothing more than a barely perceptible dot shifting slowly against the background stars over hours or days of observation. 2 astronomers decided to find out whether the theoretical belt was real. Dave Jewett and Jane Liu began their search in 1987 at the University of Hawaii using telescopes on Mauna Kea. The task was almost absurdly difficult. They were looking for objects so faint that they hovered at the very edge of detectability, points of light millions of times dimmer than what the naked eye can see. They had no guarantee anything was out there at all. The search required taking deep exposures of small patches of sky near the plane of the solar system, then comparing images taken hours or nights apart to see if any faint dot had moved. A moving dot against a fixed background of stars meant something was orbiting the Sun in the outer solar system. A stationary dot was just another star. Night after night, year after year, they scanned and compared. The early results were discouraging. Nothing moved. The outer solar system appeared to be exactly what conventional wisdom suggested. Empty. 5 years of searching produced 5 years of nothing. Then, on the night of August 30th, 1992, they found it. A faint object, barely visible even in their long exposure images, was shifting position against the background stars at exactly the rate expected for something orbiting at roughly 44 astronomical units from the Sun. It was not an asteroid. It was not a comet. It was not a known planet or moon. It was a new class of object, orbiting in the exact region where the theoretical Kuiper Belt was supposed to exist. They designated it 1992 QB1. That single detection cracked open a door that could never be closed again. Within months, Jewett and Liu found a second object, then a third. Other teams joined the hunt with their own telescopes and survey programs. Within the next decade, improved CCD cameras, larger telescope apertures, and dedicated survey strategies revealed a population of outer solar system objects that nobody had directly seen before. Hundreds of new objects appeared in the data, each one a faint speck, drifting slowly through the darkness beyond Neptune. The Kuiper Belt went from theoretical to undeniable. The outer solar system was not empty. It was populated by a vast, distributed collection of frozen bodies that had been orbiting unseen for the entire history of human astronomy. As of today, astronomers have catalogued over 3,000 Kuiper Belt objects, and the total population of objects larger than 1 kilometre is estimated to be in the hundreds of millions. Models suggest there may be more than 100,000 objects in the belt, larger than 100 kilometres in diameter alone. The Kuiper Belt is not a sparse scattering of a few icy rocks. It is one of the most heavily populated structural zones in the entire solar system. It contains more individual objects than the asteroid belt between Mars and Jupiter, and it spans a volume of space so enormous that the asteroid belt could fit inside it thousands of times over. Yet most people, if asked to name the major regions of the solar system, would mention the inner planets, the asteroid belt, the outer planets, and then stop. The Kuiper Belt barely registers. It exists in a strange perceptual blind spot, acknowledged by science but absent from the mental model that most humans carry of their own cosmic home. What makes this region fundamentally different from the asteroid belt is not just its size, but its composition, its temperature, and its relationship to the history of the solar system. The asteroid belt, located between Mars and Jupiter at roughly 2 to 3.3 astronomical units from the Sun, consists primarily of rocky and metallic objects. Most asteroids are composed of silicate minerals, iron, nickel, and other materials that can survive the relatively warm temperatures of the inner solar system. The largest asteroid, Ceres, measures about 940 kilometers in diameter and was reclassified as a dwarf planet. The total mass of the entire asteroid belt is remarkably small, roughly 4% of the Moon's mass. Despite its dramatic appearance in movies and illustrations, the asteroid belt is sparse and lightweight. The Kuiper Belt is a different animal entirely. Its objects are composed primarily of frozen volatiles, water ice, methane ice, ammonia ice, nitrogen ice, and carbon monoxide ice. These are materials that can only remain solid at the brutally low temperatures found beyond Neptune, where the Sun's warmth has faded to nearly nothing. Surface temperatures on Kuiper Belt objects hover around -220 to -240 degrees Celsius. At those temperatures, substances that exist as gases or liquids anywhere in the inner solar system freeze into rock-hard solids. Methane, which you might know as natural gas, becomes ice. Nitrogen, which makes up 78% of the air you breathe, freezes into a translucent solid. Even carbon monoxide, a gas on Earth, locks into a crystalline frost. These ices are not incidental. They are the defining characteristic of the Kuiper Belt, and the key to why this region matters so deeply to planetary science. The frozen materials in the Kuiper Belt are leftover building blocks from the formation of the solar system itself. 4.5 billion years ago, the Sun was surrounded by a vast rotating disk of gas and dust called the solar nebula. Closer to the Sun, where temperatures were high, only rocky and metallic materials could condense into solid grains. Those grains clumped together to form the terrestrial planets. Farther out, beyond a boundary called the frost line, temperatures dropped low enough for ices to condense alongside rock. The giant planets, Jupiter, Saturn, Uranus, and Neptune, formed in this colder zone, accumulating massive envelopes of hydrogen and helium gas around solid cores. But not everything in the outer solar system got incorporated into a planet. Beyond Neptune, the density of material in the solar nebula was too low and the orbital periods too long for a large planet to assemble. The building blocks remained as individual chunks, frozen in place, orbiting slowly in the dim outer reaches. These are the Kuiper Belt objects. They are planetary construction debris, leftovers, pieces that never got the chance to become part of something bigger. This makes them extraordinarily valuable to science. Because the Kuiper Belt is so far from the Sun and so cold, these objects have been preserved in a state remarkably close to their original condition. They are fossils of the solar nebula, frozen time capsules that record the chemistry and physics of the early solar system. Studying them is like studying the ingredients list of a recipe after the meal has already been cooked and eaten. The planets formed and evolved. The Kuiper Belt objects stayed raw. But there is a complication in this story that reshapes the entire picture. The Kuiper Belt does not simply sit passively in place, unchanged since the solar system formed. It has been sculpted, stirred, and reorganized by the gravitational influence of the giant planets, particularly Neptune. In the early solar system, the giant planets did not occupy their current orbits. They migrated. Jupiter moved slightly inward. Saturn, Uranus, and Neptune moved outward. Neptune's outward migration was particularly dramatic. As it swept through the outer solar system, Its gravity interacted with the disk of icy planetesimals, scattering some objects inward, flinging others outward, and trapping many into specific orbital patterns called resonances. A resonance occurs when two orbiting bodies exert regular, periodic gravitational influence on each other because their orbital periods form a simple ratio. The most famous resonance in the Kuiper Belt is the 2-to-3 resonance with Neptune. Objects in this resonance complete 2 orbits around the Sun for every 3 orbits Neptune completes. This gravitational lockstep stabilizes their orbits and protects them from close encounters with Neptune. Pluto is the most famous object in this resonance. It is not alone. Hundreds of other icy bodies share the same orbital pattern. Scientists call these objects Plutinos, and they represent one of the major dynamical populations within the belt. Other populations exist as well. The classical Kuiper Belt, sometimes called the cold classical belt, consists of objects on relatively circular, low inclination orbits between roughly 42 and 47 astronomical units. These objects appear to have avoided the worst of Neptune's gravitational disruption, surviving in orbits that have changed little since the belt's earliest days. The hot classical population occupies similar distances but with higher orbital inclinations and eccentricities, suggesting these objects were scattered into their current positions by gravitational interactions during the migration era. Beyond the main belt lies the scattered disk, a population of objects on highly eccentric orbits that can carry them from as close as 30 astronomical units to several hundred astronomical units from the Sun. These objects were flung outward by Neptune encounters and now occupy a diffuse cloud that overlaps with and extends far beyond the classical belt. Some scientists classify scattered disk objects as part of the broader Kuiper Belt family. Others treat them as a distinct population. The boundary is debated, but the physical reality is clear. The Sun's outer domain is populated by a complex, layered distribution of icy bodies shaped by billions of years of gravitational interaction. Neptune is the architect of this entire structure. Without Neptune's migration and its ongoing gravitational influence, the Kuiper Belt would look completely different. The resonances would not exist. The populations would not be separated. The sharp inner edge of the belt, which coincides almost exactly with Neptune's orbital distance, would not be so cleanly defined. Neptune does not just sit next to the Kuiper Belt. It carved the belt into its current form. This relationship between Neptune and the Kuiper Belt is one of the most important structural features of the outer solar system. It tells scientists that the solar system underwent a violent reorganization early in its history. The planets did not simply form in place and stay put. They migrated, interacted, and rearranged the architecture of the entire system. The Kuiper Belt preserves the scars of that upheaval. Every resonant population, every gap in the orbital distribution, every cluster of objects on similar trajectories is a forensic clue pointing back to events that happened over 4 billion years ago. And this is where the story starts to feel uncomfortable. Because everything described so far, the size, the composition, the dynamical complexity, is not exotic speculation. It is confirmed observational science supported by decades of telescope surveys, spacecraft data, and computer modelling. The Kuiper Belt is as real and as structurally important as the asteroid belt or the system of giant planets. It is a major zone of the solar system. And yet it occupies almost no space in the popular imagination. Ask yourself how many times you have seen a diagram of the solar system that accurately represents the Kuiper Belt, not a tiny label at the edge of the poster, an actual depiction that shows its true scale relative to the planetary zone. The answer, for almost everyone, is never. Classroom models compress the solar system to fit on a page. They show the planets at roughly even intervals, shrink the distances, and stop at Neptune or Pluto. The Kuiper Belt, when it appears at all, shows up as a faint dotted arc at the margin, an afterthought, a footnote. This is not a trivial omission. It is a distortion of reality that shapes how billions of people understand the structure of their own solar system. If the planetary zone were drawn to scale alongside the Kuiper Belt, the familiar 8 planets would cluster in the inner portion of the diagram, while the icy belt extended outward for twice their combined span. The solar system would look less like a neat row of planets and more like a dense core surrounded by an enormous frozen halo. The distortion matters because it creates a false sense of completeness. People believe the solar system has been mapped, explored, and understood. The planets have names. Spacecraft have visited them. Photographs exist. The story feels finished, but the Kuiper Belt is not finished. It is barely started. As of today, only one spacecraft has ever visited the Kuiper Belt for close-range science. NASA's New Horizons, launched in 2006, flew past Pluto in 2015 and past a small Kuiper Belt object called Arrokoth in 2019. Those two flybys represent the entire history of direct human exploration in a region that spans billions of miles. No orbiter has ever circled a Kuiper Belt object. No lander has ever touched one. No rover has ever driven across one. The Kuiper Belt has been visited the way a driver on a highway glances at a town through the window without stopping. Meanwhile, the ground-based and space-based telescopes that detect Kuiper Belt objects face severe limitations. These objects are extraordinarily faint. A typical Kuiper Belt object, 100 kilometers in diameter, reflects so little sunlight at its enormous distance that it appears roughly 10 million times fainter than what the naked eye can see. Detecting them requires large telescopes, long exposure times, and sophisticated image processing techniques that can pick out a slowly drifting dot against a field of stationary stars. The surveys are improving, and the Vera C hit. Rubin Observatory, which recently began operations in Chile, is expected to discover approximately 35,000 new Kuiper Belt objects over the next decade, increasing the known population nearly tenfold. But even this dramatic expansion will represent only a fraction of the total population. Most of the Kuiper Belt remains unseen. The sheer volume of space involved makes this inevitable. The Kuiper Belt is not a thin ring. It is a thick torus, a three-dimensional donut of space, extending above and below the plane of the solar system. Its volume is staggeringly large. If you took the entire region from 30 to 50 astronomical units and calculated the total cubic mileage, the number would be so large it would carry more zeros than most calculators can display. For comparison, the volume of space enclosed by Earth's orbit around the Sun is approximately 3.4 times 10 to the 24th cubic miles. The Kuiper Belt's volume is roughly 100,000 times larger than that. 100,000 times more space than the entire sphere that contains Earth's yearly path around the Sun. Try to hold that ratio in your mind. Take every cubic mile of space inside Earth's orbit, every point through which our planet passes over the course of a full year, every region of vacuum between us and the Sun. That volume is not small. It is a sphere 93 million miles in radius. Light itself needs 8 minutes to cross from its center to its edge. Now multiply it by 100,000. That is the Kuiper Belt. A region so voluminous that the entire orbital sphere of the Earth, which already feels incomprehensibly vast to any human being who has ever tried to picture it, vanishes inside the belt the way a thimble of water vanishes inside a tanker truck, and most of that volume is empty. This is one of the Kuiper Belt's most disorienting features. Despite containing hundreds of thousands or even millions of objects, the distances between them are so vast that the belt is overwhelmingly vacuum. The average separation between large Kuiper Belt objects is on the order of tens of millions of miles. To put that in perspective, the entire distance between the Earth and Mars at their closest approach is roughly 34 million miles. That is roughly the gap between neighbouring Kuiper Belt objects, each one drifting through its own private expanse of nothing, separated from the next, by a void wide enough to swallow an inner planet's entire orbit. This emptiness is not the kind of emptiness you experience on a dark night in the countryside. It is not even the emptiness of interplanetary space between Mars and Jupiter, where at least the sun still blazes overhead and the planets still shine as bright points in the sky. The emptiness of the Kuiper Belt is something more total. It is emptiness on a scale that eliminates context. There are no landmarks, no reference points, no way to gauge distance or direction without instruments. The inner solar system, with its glowing sun, its bright planets, and its relatively compact dimensions, provides a sense of place. You can look up from any inner solar system body and see evidence that you belong to a system, a structured collection of objects sharing a gravitational neighborhood. The Kuiper Belt provides no such comfort. Its objects are so widely separated that each one exists in a private cosmos of empty space, connected to its neighbors only by the mathematics of orbital mechanics, never by anything visible, tangible, or immediate. It is a wilderness in the most literal sense, a region where the structures that anchor human perception of space begin to dissolve. And this is only the beginning. The Kuiper Belt's existence does not merely extend the solar system. It changes the meaning of the solar system. It transforms our cosmic home from a tidy arrangement of planets orbiting a star into something far larger, far stranger, and far less comprehensible. The familiar inner system becomes the bright, warm lobby of a building, whose true extent stretches into darkness in every direction. What lives in that darkness is even more surprising than the emptiness itself. The Kuiper Belt is not just a featureless zone of scattered ice. It contains worlds. Actual worlds, with surfaces, with geology, with moons, with histories stretching back to the birth of the sun. Some of these worlds are hundreds of kilometers across. A few rival the size of small planets. And what scientists have learned about them in recent years has shattered assumptions that were held for decades. What those frozen worlds look like, how they formed, and why they matter, is where this story takes its next turn. For decades, Pluto was treated as a loner, the ninth planet, the runt at the back of the line. Textbooks placed it at the end of the solar system like a period at the end of a sentence, small, distant, and isolated. Students learned its name alongside Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, and the implication was always the same. Pluto was the final world. Beyond it, nothing. That story was never true. And the moment astronomers began discovering what actually surrounds Pluto, the entire framing collapsed. Pluto is not a loner. It is a local. One resident among a vast population of icy bodies orbiting in the same broad zone of the outer solar system. It is the most famous member of the Kuiper Belt, but it is not alone, and it is not even the most massive. It is embedded in a community of frozen worlds that stretches across billions of miles, and the sheer diversity of that community is one of the most underappreciated facts in modern planetary science. Begin with the dwarf planets. Pluto has a diameter of roughly 2,370 kilometers. It is smaller than Earth's moon. Its surface is a patchwork of nitrogen ice, methane frost, and carbon monoxide ice, sculpted by processes that scientists are still working to understand. It has 5 known moons, the largest of which, Charon, is so big relative to Pluto that the two orbit a common center of gravity located in empty space between them. The Pluto-Charon system is sometimes described as a binary world rather than a planet and moon, a gravitational partnership unique among known solar system bodies. But Pluto is not the only dwarf planet in the Kuiper Belt. Eris, discovered in 2005, has a diameter of approximately 2,326 kilometers, making it almost the same size as Pluto, though slightly more massive. Eris orbits much farther out, on a highly eccentric path that carries it from about 38 astronomical units at its closest approach to the Sun, out to nearly 98 astronomical units at its farthest, well beyond the main belt into the scattered disk. Its surface is covered in a bright frost of frozen nitrogen and methane, giving it one of the highest albedos of any body in the solar system. It has one known moon, Dysnomia, roughly 600 kilometers across. The discovery of Eris was the direct trigger for Pluto's reclassification. If Pluto was a planet, then Eris had to be one too. Rather than add a 10th planet, the International Astronomical Union created the dwarf planet category in 2006, placing both objects in it. Makemake, discovered in 2005, orbits at an average distance of about 45.8 astronomical units. Its diameter is approximately 1,430 kilometers. It has a provisional moon designated S/2015 (136472) 1, detected in 2015 by the Hubble Space Telescope. Make's surface is dominated by frozen methane and ethane, with indications that the methane ice exists in large crystal grains, suggesting a surface that has been processed by long exposure to weak ultraviolet radiation from the distant sun. Haumea is one of the strangest objects in the solar system. It has a diameter measured along its longest axis of roughly 2,320 kilometers, but it is not spherical. Haumea spins so rapidly, completing one rotation in under 4 hours, that centrifugal force has stretched it into an elongated ellipsoid, shaped roughly like a flattened rugby ball. This extreme rotation rate is thought to be the result of a massive ancient collision that also produced a family of smaller icy fragments sharing similar orbits, the only known collisional family in the Kuiper Belt. Haumea has 2 known moons, Hiaka and Namaka, and in 2017, astronomers discovered that it possesses a ring system, the first ring ever detected around a trans-Neptunian object. Then there is Quaoar, orbiting at about 43 astronomical units with a diameter of roughly 1,110 kilometers. Quaoar is smaller than the largest dwarf planets but significant in its own right. In 2022, astronomers using stellar occultation data detected a ring around Quaoar, located at a distance of roughly 4,100 kilometers from the object's center. This discovery stunned the scientific community, because the ring orbits well beyond Quaoar's Roche limit, the boundary inside which tidal forces should prevent ring material from clumping together into a moon. According to conventional theory, material that far out should coalesce rather than remain a ring. The discovery challenged established models of ring dynamics and remains an active area of investigation. More recently, in 2025, astronomers reported evidence suggesting Quaoar may have an additional moon, making it a potentially even more complex system than previously understood. These 5 objects, Pluto, Eris, Make, Haumea, and Quaoar, are simply the most prominent members of a much larger population. Hundreds of other Kuiper Belt objects exceed 200 kilometers in diameter. Many of these have moons. Some likely have complex surface compositions. A few may possess subsurface oceans kept liquid by trace amounts of internal heat from radioactive decay, though this remains speculative for most. What is not speculative is their sheer number. The Kuiper Belt contains more dwarf planet candidates than any other region of the solar system, and the actual total of large bodies almost certainly exceeds current catalogues by a wide margin. This concentration of worlds beyond Neptune forces a reconsideration of what the solar system really is. The familiar inner system, from Mercury to Neptune, contains 8 major planets, a handful of dwarf planets, and a few 100,000 asteroids. The Kuiper Belt, by contrast, contains multiple dwarf planets, potentially hundreds of thousands of objects larger than 100 kilometers, and billions of smaller icy bodies. In terms of population count, the outer solar system overwhelms the inner. The region most people ignore contains more individual worlds than the region most people study. But counting objects only tells part of the story. Understanding how they got there and what they reveal about the solar system's past is where the Kuiper Belt becomes truly consequential. The objects in the Kuiper Belt did not appear randomly. They were placed into their current orbits by a sequence of events that reshaped the entire solar system during its first billion years. The leading model for this reshaping is commonly known as the Nice model, named after the French city where it was developed. The Nice model proposes that the 4 giant planets originally formed in a more compact configuration, closer together and closer to the Sun than their current positions. Interactions between the planets and a massive disk of leftover planetesimals eventually destabilized this arrangement, triggering a period of chaotic orbital migration. During this upheaval, Neptune moved dramatically outward, sweeping through the primordial disk of icy bodies. The migration was not instantaneous. It unfolded over tens of millions of years, a slow gravitational plough pushing through a dense field of frozen debris. As Neptune advanced outward, its gravity interacted with every icy body it encountered. Some objects were flung inward, becoming the source of a period of heavy bombardment that cratered the Moon and the inner planets. Others were flung outward into highly eccentric orbits, populating what is now the scattered disk. Still others were captured into orbital resonances with Neptune, locked into gravitational patterns that stabilized their orbits and preserved them for billions of years. The scale of disruption was extraordinary. Before Neptune's migration, the outer solar system contained a massive disk of icy planetesimals stretching from roughly 15 to 30 astronomical units, dense with material, thick with objects, populated by trillions of small frozen bodies that had been quietly orbiting since the Sun's birth. Neptune's outward march tore through this disk like a hand sweeping across a table covered in marbles. Vast numbers of objects were ejected entirely from the solar system, flung onto escape trajectories that sent them tumbling into interstellar space, lost forever. Others were hurled inward, raining down on the inner planets in a bombardment so intense that it resurfaced entire worlds. The craters that scar the Moon's face today, the ancient impact basins visible on Mercury and Mars, many of these may trace back to icy bodies that were dislodged from the outer disk during this era of planetary migration. What remained after the chaos subsided was a fraction of the original population. The Kuiper Belt as it exists today is not the primordial disk. It is the debris field left behind after Neptune's migration scattered most of the original material. Estimates suggest that the current Kuiper Belt contains only a few % of the mass that originally occupied the outer disk. The rest was lost, ejected, or consumed. The belt we observe is a remnant, a survivor population that endured the gravitational upheaval and settled into stable configurations. This means the Kuiper Belt is simultaneously ancient and young. Its objects are ancient, composed of materials that condensed from the solar nebula 4.5 billion years ago, but their orbital arrangement is younger, imposed by Neptune's migration during a period of dynamical chaos that occurred roughly 4 billion years ago. The objects are old, their addresses are newer. This distinction matters because it means the Kuiper Belt's orbital structure carries information not just about where things formed, but about how the entire solar system rearranged itself in the aftermath of planet formation. But this remnant is not uniform. Its different populations, the cold classical belt, the hot classical belt, the resonant populations, and the scattered disk, each record a different chapter in the story of Neptune's migration and the solar system's violent rearrangement. Reading these populations is like reading geological strata in a canyon wall. Each layer tells you something about a different era. The cold classical belt is particularly precious. Objects in this population occupy low inclination, nearly circular orbits clustered between about 42 and 47 astronomical units. Their orbits suggest they formed roughly in place and were never significantly disturbed by Neptune's migration. These are the least processed, most primordial objects in the solar system. Their compositions, their surfaces, and their physical structures preserve conditions from the solar nebula with minimal alteration. They are as close to original construction material as anything in the solar system gets. And this is where the story of shape becomes critical. In 2019, when New Horizons flew past the Kuiper Belt object Arrokoth, scientists got their first close look at a cold classical object. What they saw was unlike anything previously observed in the solar system. Arrokoth is a contact binary, two roughly spherical lobes joined at a narrow neck, forming a shape that immediately earned comparisons to a snowman. The larger lobe is roughly 22 kilometers across. The smaller lobe is roughly 14 kilometers. The two components are remarkably smooth, with very few impact craters, suggesting a surface that has remained largely undisturbed for billions of years. The color is uniformly reddish, consistent with long-term irradiation of organic-rich ices by cosmic rays and ultraviolet light. The shape told scientists something extraordinary. Arrokoth did not form through a violent collision. The two lobes came together gently, at speeds of only a few meters per second, slow enough that a person could jog faster. This gentle merger implied that the object formed through a process called gravitational collapse, where a cloud of small particles in the solar nebula concentrated under its own gravity, separated into two clumps, orbited each other briefly, and then spiraled together into contact. The resulting body preserved the shapes of both original clumps almost perfectly, like two scoops of ice cream placed carefully together and then frozen solid. This was a landmark finding. It supported a theoretical model of planetesimal formation called the streaming instability hypothesis, which proposes that small solid particles in a protoplanetary disk can concentrate into dense filaments through aerodynamic interactions with the surrounding gas. When these concentrations reach a critical density, they collapse gravitationally into bound objects, bypassing the slow, step-by-step process of dust grains sticking together one at a time. The streaming instability can produce binary pairs naturally, which then merge into the bilobed shapes observed throughout the Kuiper Belt. And Arrokoth is not an outlier. Observations from Earth suggest that contact binaries are common in the Kuiper Belt. Light curve studies, which track how an object's brightness changes as it rotates, reveal that a significant fraction of Kuiper Belt objects show the double-peaked brightness patterns characteristic of elongated or bilobed shapes. Estimates suggest that roughly 10 to 30% of small Kuiper Belt objects may be contact binaries. The frozen outer solar system is populated with snowman-shaped relics of gravitational collapse, each one a fossil of the planet-forming process preserved in deep freeze for over 4.5 billion years. In February of 2026, a study published in the monthly notices of the Royal Astronomical Society provided the most detailed simulations yet of how these shapes form. Jackson Barnes, a graduate student at Michigan State University, demonstrated through computer models that a spinning cloud of pebble-sized material can collapse, split into two gravitationally bound lobes, and then gently bring those lobes into contact without shattering either one. The simulations produced a variety of bilobed shapes with different lobe sizes and proportions, matching the diversity of contact binaries observed in the belt. The results strengthened the case that objects like Arrokoth formed directly as two-lobed bodies, rather than assembling later through lucky low-speed collisions. A separate finding added another layer. In early 2025, observations from the Hubble Space Telescope revealed that a Kuiper Belt system, previously identified as a binary, two objects orbiting each other, showed orbital dynamics consistent with a hidden third member too close to its companion to resolve visually. If confirmed, this would make it only the second known triple system in the Kuiper Belt. The larger implication is significant. The streaming instability hypothesis predicts that gravitational collapse should naturally produce not just binaries but also higher-order multiples. Finding triple systems would validate that prediction and suggest many more hidden triples exist throughout the belt, waiting for more sensitive instruments to reveal them. These discoveries matter because they transform the Kuiper Belt from a passive collection of debris into an active record of how planets form. Every contact binary is a data point. Every binary orbit encodes information about the conditions in the solar nebula when it collapsed. Every surface composition records the chemistry of the protoplanetary disk at that specific distance from the young sun. The Kuiper Belt is not a junkyard. It is an archive, and scientists have barely begun reading it. But the Kuiper Belt's significance extends beyond ancient history. It also connects directly to objects that visit the inner solar system today. Short-period comets, specifically the Jupiter family comets that return to the Sun's vicinity on timescales of roughly 20 years or less, originate primarily from the Kuiper Belt. Familiar examples include Comet Tempel 1, visited by NASA's Deep Impact mission, and Comet 67P, Churyumov-Gerasimenko, orbited and studied by the European Space Agency's Rosetta spacecraft. Dozens of these Jupiter family comets have orbits consistent with Kuiper Belt origins. These comets are icy bodies that were gravitationally perturbed out of the belt, typically through interactions with Neptune, and nudged into orbits that bring them close to the Sun. As they approach the inner solar system, solar heating sublimates their surface ices, producing the glowing tails that humans have observed and recorded for thousands of years. The mechanism works like a slow conveyor belt. Neptune's gravity occasionally destabilizes Kuiper Belt objects near the inner edge of the belt, nudging them onto orbits that cross Neptune's path. From there, gravitational encounters with the giant planets can progressively alter the object's orbit, pulling its closest approach to the Sun inward over millions of years. Eventually, the object enters the inner solar system, where solar radiation activates its volatiles and transforms it into a visible comet. The transformation itself is violent and strange. For billions of years, the object drifted in the deep freeze of the outer solar system, its surface locked at temperatures near -230 degrees, its volatile ices sealed beneath a crust of radiation-processed tholins. Nothing happened to it. Nothing changed. Then, over the course of millions of years, its orbit slowly tightens. Each pass brings it fractionally closer to the Sun. At first, the additional warmth is negligible, a few fractions of a degree over centuries, but as the orbit contracts, the effect accumulates. Somewhere around 5 to 10 astronomical units from the Sun, roughly the distance of Jupiter to Saturn, the surface temperature begins to rise enough for the most volatile ices to respond. Carbon monoxide sublimating first, then carbon dioxide. Molecules that have been frozen solid since before the Earth existed begin to stir, transitioning directly from ice to gas without ever passing through a liquid phase. As the object crosses inside Jupiter's orbit, the transformation accelerates. The Sun's radiation, now hundreds of times stronger than anything the object experienced in the Kuiper Belt, penetrates the dark surface crust and reaches the volatile ices beneath. Gas erupts through cracks and vents in the surface, carrying dust particles with it in jets that spray outward into the vacuum. The object develops a coma, a diffuse cloud of gas and dust surrounding the nucleus, glowing faintly in reflected sunlight. As it continues inward, solar wind and radiation pressure push the coma's material into long streaming tails, one made of ionized gas pointing directly away from the Sun, another made of dust curving gently along the orbital path. The comet has awakened. After 4.5 billion years of frozen stillness, it is being dismantled by the very star that created it. This process means the comets you see in the night sky are messengers from the Kuiper Belt. They carry icy material that has been stored at temperatures near absolute zero for billions of years, material that preserves the chemical fingerprint of the early solar system. When a comet's tail streams across the sky, you are watching ancient Kuiper Belt ice sublimate in real time, releasing molecules that formed before the Earth existed. The connection to comets also hints at the Kuiper Belt's role in delivering water and organic compounds to the inner solar system. During the period of heavy bombardment roughly 4 billion years ago, when the giant planet's migration was scattering icy bodies inward, a rain of cometary material fell on the young Earth. Some scientists propose that a significant fraction of Earth's water may have been delivered by cometary impacts during this era. The isotopic ratios of hydrogen in some comets match the ratios found in Earth's oceans, though the evidence remains debated, and the picture is complicated by contributions from other sources such as water-rich asteroids. Whether or not comets delivered most of Earth's water, the broader point stands. The Kuiper Belt is not an isolated region with no connection to the inner solar system. It is a reservoir that has been feeding material inward for billions of years, shaping the chemistry and evolution of worlds much closer to the Sun. The diversity of the Kuiper Belt extends beyond physical shapes and orbital dynamics. The surface compositions of Kuiper Belt objects vary dramatically depending on size, distance, and dynamical history. The largest objects like Pluto, Eris, and Makemake have surfaces dominated by frozen methane, nitrogen, and carbon monoxide. These volatile ices are light enough to sublimate and redeposit over seasonal cycles, creating active surface processes even at extreme distances from the Sun. Pluto's nitrogen glaciers flow under their own weight, albeit at glacial speeds measured in centimeters per year. Eris's surface appears uniformly bright, possibly resurfaced by condensing nitrogen frost as the dwarf planet moves through the colder portions of its eccentric orbit. Smaller objects tend to have surfaces dominated by water ice mixed with dark, reddish organic compounds called tholins. Tholins form when simple molecules like methane and nitrogen are irradiated by ultraviolet light and cosmic rays over millions of years. The result is a complex tarry residue that coats surfaces with a distinctive brick-red colour. Many Kuiper Belt objects appear red or ultra-red in telescopic observations, and tholins are the leading explanation. These organic-rich surfaces are scientifically valuable because they represent a form of abiotic chemistry, complex carbon-based molecules assembled without biology, produced by nothing more than radiation, acting on simple ices over cosmic timescales. The colour distribution of Kuiper Belt objects is not random. Cold classical objects tend to be redder than other populations. Hot classical and scattered disk objects tend to be greyer or more neutral in colour. This colour divide correlates with dynamical history. The red cold classical objects formed in place and were never heated or disturbed. The greyer objects were scattered from regions closer to the Sun, where warmer temperatures may have altered their surface chemistry before they were flung outward. Colour, in the Kuiper Belt, is a tracer of origin. Some objects defy easy categorization. In 2018, observations identified a Kuiper Belt object called 2004 EW95 as having a carbon-rich surface composition, unlike any other known trans-Neptunian object. Its spectral signature suggested the presence of ferric oxides and phyllosilicates, materials associated with carbonaceous asteroids from the inner solar system. If confirmed, this object may have originally formed much closer to the Sun and been ejected outward during the period of planetary migration. It would represent a piece of the inner solar system stranded in the frozen outer reaches, a traveller from a warmer past. The compositional diversity of the Kuiper Belt complicates any simple narrative. This is not a uniform population of identical ice balls. It is a mixed community of objects with different formation locations, different migration histories, different surface chemistries, and different internal structures. Some may be solid rock-ice mixtures, others may be loosely bound rubble piles. A few of the largest may have differentiated interiors, with rocky cores surrounded by icy mantles and possibly thin subsurface layers of liquid water or ammonia water solution kept from freezing by residual radioactive heat. This internal complexity connects to one of the Kuiper Belt's most tantalizing unanswered questions. Could any of these objects harbor conditions suitable for prebiotic chemistry, or even rudimentary biological processes? The question may sound absurd given the extreme cold and distance from the Sun, but the discovery of subsurface oceans on moons like Europa and Enceladus, worlds also far from the Sun and heated primarily by tidal forces, has expanded the definition of habitable environments. If a large Kuiper Belt object retains enough internal heat to maintain a liquid layer beneath its ice shell, and if that liquid is in contact with a rocky core providing chemical energy, then the theoretical conditions for life are met, however tenuously. No evidence currently supports the existence of life in the Kuiper Belt. The idea remains speculative. But the fact that it can be seriously discussed at all reflects how much the scientific understanding of this region has matured. 30 years ago, Kuiper Belt objects were presumed to be inert chunks of dirty ice. Today they are recognized as complex, diverse, and scientifically rich worlds with geological processes, organic chemistry, and possibly even liquid interiors. The Kuiper Belt also serves as a gravitational detective story that may point to an unseen massive body. For years, astronomers have noted that certain distant Kuiper Belt objects on highly eccentric orbits share unusual orbital alignments, clustering in ways that are difficult to explain by chance alone. This pattern has fueled the hypothesis of a possible undiscovered planet, sometimes referred to as Planet 9, orbiting far beyond the main belt at distances of several hundred astronomical units. In September of 2025, a survey analysis published in the monthly notices of the Royal Astronomical Society proposed that an unseen planet, at least 25 times more massive than Pluto, might reside within the Kuiper Belt region itself, based on orbital clustering detected in a new dataset. The existence of such a planet remains unconfirmed. Searches using ground-based and space-based telescopes have not yet detected it directly. Some researchers argue that the observed orbital clustering is a statistical artifact caused by observational biases in how surveys detect faint distant objects. Others maintain that the clustering is real and requires a gravitational explanation. The debate is vigorous, unresolved, and unlikely to be settled until more complete surveys, particularly from the Vera Rubin Observatory, provide a less biased census of the outer solar system. Whether or not Planet 9 exists, the hypothesis illustrates a broader truth about the Kuiper Belt. This region still holds fundamental surprises. Its population is incompletely catalogued. Its dynamical structure is only partially understood. Its largest members may not yet have been discovered. The Kuiper Belt is not a solved problem filed away in the back of a textbook. It is an active frontier of discovery, where major revisions to our understanding of the solar system remain entirely plausible. And all of this, every dwarf planet, every contact binary, every scattered disk object, every candidate planet lurking in the orbital data, exists in conditions so extreme that they strain the human ability to process them. Knowing what lives in the Kuiper Belt is one thing. Reckoning with what it actually feels like out there, with the cold, the dark, the distance, and the silence, is something else entirely. That reckoning is about to arrive, because in 2015, a spacecraft no heavier than a motorcycle crossed the threshold and sent back the first direct evidence of what the Kuiper Belt looks like up close. What it found changed everything. Scientists thought they knew about the frozen outer frontier, and what it measured on its way through told them the frontier may be far larger than anyone had imagined. On the 14th of July, 2015, a spacecraft the size of a baby grand piano completed a journey of 9.5 years and 3 billion miles to deliver humanity its first close look at the Kuiper Belt. New Horizons arrived at Pluto travelling at roughly 14 kilometers per second, so fast that there was no possibility of slowing down to orbit. The entire encounter was a flyby, a single high-speed pass during which every instrument aboard fired continuously, collecting data that would take over a year to transmit back to Earth. The closest approach brought the spacecraft within 12,500 kilometers of Pluto's surface. The signal confirming a successful flyby took 4 hours and 25 minutes to reach mission control at the Johns Hopkins Applied Physics Laboratory, travelling at the speed of light across the solar system. What came back in the data changed the way scientists think about the outer solar system. The expectation, going in, was that Pluto would look like a frozen relic. Most models predicted a battered, cratered surface, geologically dead for billions of years. With a diameter of only 2,370 kilometers and a surface temperature hovering around -230 degrees Celsius, there seemed to be no mechanism capable of driving geological activity. Pluto was too small, too cold, too far from any energy source. It should have been an inert ball of ice with a face scarred by billions of years of impacts. That is what decades of indirect observation and theoretical modelling suggested. The images told a completely different story. The first high-resolution photographs revealed a world of staggering geological complexity. The western hemisphere of Pluto is dominated by a vast, heart-shaped feature now officially named Tombaugh Regio, after Pluto's discoverer, Clyde Tombaugh. The left lobe of this heart contains a massive plain of nitrogen ice called Sputnik Planitia, a basin roughly 1,000 kilometers across and several kilometers deep. Sputnik Planitia is one of the smoothest surfaces ever observed in the solar system. It contained no visible impact craters. In a region of space where cratering should be the dominant surface process, a blank slate this large can mean only one thing. The surface is young. Something erased the craters. Something is still active. Scientists determined that Sputnik Planitia is a dynamic landscape. The nitrogen ice that fills the basin is not static. It moves. The surface is divided into irregular polygonal cells, each roughly 30 to 40 kilometers across, separated by shallow troughs. These cells are the surface expression of convective overturn in the nitrogen ice below. Warmer ice rises from the interior of the basin, spreads across the surface, cools and sinks at the edges, creating a slow churning motion similar to the convective patterns seen in a pot of gently heated water. The process operates on timescales of roughly 500,000 years per overturn cycle, slow by human standards but geologically vigorous. For a world this cold and this far from the sun, around the edges of Sputnik Planitia, the terrain changes dramatically. Mountain ranges of water ice rise abruptly from the basin floor, reaching heights of 3 to 4 kilometers. Water ice at Kuiper Belt temperatures behaves mechanically like rock, forming rigid structural features that can support steep slopes. These mountains are not volcanic. They are blocks of water ice bedrock that border the nitrogen ice basin, standing like frozen sentinels along the edge of a glacial plain. Elsewhere on Pluto's surface, New Horizons found evidence of even more diverse geology. Dark reddish patches near the equator are coated in tholins, complex organic molecules produced by ultraviolet radiation acting on methane and nitrogen in Pluto's thin atmosphere. Blade-like ridges of methane ice, called penitentes, extend for hundreds of kilometers in some regions, their sharp profiles shaped by sublimation patterns driven by the angle of incoming sunlight. Impact craters of varying sizes and degradation states pockmark much of the surface outside Sputnik Planitia, but even these show signs of modification, partially filled by ice deposits, softened by sublimation, or cut through by tectonic fractures. Those fractures are among the most telling features New Horizons observed. Long extensional faults stretch across Pluto's surface, some running for hundreds of kilometers. These cracks indicate that Pluto's outer shell has been pulled apart, consistent with internal expansion. One explanation is that a subsurface ocean, liquid water trapped between the rocky core and the outer ice shell, has been slowly freezing over geological time. Water expands when it freezes. As the ocean gradually solidifies from the outside in, the expanding ice pushes outward against the shell, creating tensional fractures on the surface. The possibility that Pluto harbours or once harboured a subsurface ocean was one of the most consequential findings of the flyby. Thermal models developed after the encounter suggest that a layer of liquid water, perhaps mixed with ammonia as an antifreeze, could persist beneath the ice shell to the present day. The heat source would be residual radioactive decay in Pluto's rocky core, faint but sufficient to maintain a thin liquid layer at the base of the ice shell, insulated from the -230-degree surface by kilometers of frozen nitrogen and water ice. If such an ocean exists, Pluto joins a growing list of solar system worlds, including Europa, Enceladus, Titan, and Ganymede, where liquid water may persist beneath an icy exterior far from the warmth of the sun. The atmosphere New Horizons characterized added another dimension of surprise. Pluto possesses a thin but measurable atmosphere composed primarily of nitrogen, with traces of methane and carbon monoxide. The surface pressure is roughly 100,000 times lower than Earth's, barely more than a technical vacuum by terrestrial standards. But this wispy envelope of gas extends hundreds of kilometers above the surface, far higher than expected. New Horizons detected atmospheric haze layers stacked in distinct bands, visible in backlit images taken as the spacecraft looked back at Pluto after closest approach. These haze layers are composed of tiny tholin particles, created when ultraviolet light from the sun breaks apart methane molecules high in the atmosphere, triggering a cascade of chemical reactions that build increasingly complex organic compounds. These particles settle slowly toward the surface, contributing to the dark reddish deposits observed on the ground. Pluto's atmosphere is not stable. It is in a constant state of exchange with the surface ices. As Pluto moves along its eccentric 248-year orbit, its distance from the Sun varies significantly, from about 29.7 astronomical units at closest approach to 49.3 astronomical units at its farthest. This variation drives seasonal cycles in which surface ices sublimate into gas during warmer periods and refreeze onto the surface during colder ones. The atmosphere inflates and deflates over centuries, rising and falling like a slow cosmic breath. At its most distant orbital point, the atmosphere may collapse almost entirely, freezing out onto the surface as a thin frost. Charon, Pluto's largest moon, presented its own set of revelations that proved almost as scientifically disorienting as the discoveries on Pluto itself. With a diameter of roughly 1,212 kilometers, Charon is more than half the size of Pluto, making the pair more like a double world than a planet and satellite. The two are tidally locked, each presenting the same face to the other as they orbit their common center of gravity once every 6.4 days. No other known planet-moon system in the solar system exhibits this mutual locking. They orbit each other like two dancers frozen in a permanent embrace, separated by roughly 19,600 kilometers of empty space. New Horizons revealed that Charon's surface tells a very different story from Pluto's. Where Pluto is coated in volatile ices that sublimate and migrate, Charon's surface is dominated by water ice, stable and inert at these temperatures. The moon lacks the bright nitrogen and methane frosts that make Pluto's surface so visually striking. Instead, Charon presents a muted grey and brown landscape, older and more heavily cratered than the resurfaced plains of its parent world. But Charon is far from featureless. Its north pole is capped by a dark reddish deposit that scientists informally named Mordor Macula. The leading explanation for this feature connects directly to Pluto's atmosphere. Methane molecules escaping from Pluto's thin atmospheric envelope drift across the gap between the two worlds. Some of this methane reaches Charon's polar regions, where it becomes cold-trapped on the surface during the decades-long polar winter. When the pole eventually rotates back into faint sunlight, ultraviolet radiation from the distant sun processes the methane into tholins, the same complex organic residue found on Pluto's surface. Over millions of years, this cycle deposits a progressively thicker layer of dark reddish material on Charon's poles. It is atmospheric chemistry conducted across the vacuum of space between two worlds, a process with no known parallel elsewhere in the solar system. Charon's equatorial zone revealed something even more dramatic. A vast canyon system stretches across the moon's midsection, running for over 1,000 kilometers and plunging to depths of up to 9 kilometers. To put that in perspective, Earth's Grand Canyon reaches a maximum depth of roughly 1.8 kilometers. Charon's rift is 5 times deeper, cut across a world only 1/10 the diameter of Earth. The feature suggests that Charon's outer shell was subjected to tremendous extensional stress at some point in its past. The most likely explanation mirrors the one proposed for Pluto's fractures. If Charon once possessed a subsurface ocean, the gradual freezing of that ocean would have expanded the interior, stretching the crust and tearing it apart along the equator. The canyon system would be the scar of that ancient expansion, a record of internal activity on a world that should have been geologically silent from the day it formed. The possibility that both Pluto and Charon once harboured, or may still harbour, liquid water beneath their surfaces was among the most profound results of the entire mission. These are not large worlds. They orbit in a region of space so cold that nitrogen freezes into rock. The sun delivers so little energy at their distance that it cannot meaningfully warm anything, and yet the evidence points toward internal processes driven by nothing more than the slow decay of radioactive elements in their rocky cores, sufficient to maintain liquid water for billions of years. If this can happen at Pluto, the implications for the wider Kuiper Belt population are staggering. Dozens of other Kuiper Belt objects are comparable in size. If even a fraction of them share similar internal structures, the outer solar system may contain a far larger inventory of liquid water environments than anyone imagined before New Horizons arrived. Every one of these findings challenged the assumption that Kuiper Belt objects should be geologically dead. Pluto and Charon are active, complex, and scientifically rich worlds that would be headline-worthy targets in any region of the solar system. The fact that they orbit in the frozen outer wilderness only makes their complexity more remarkable. If Pluto, a body barely larger than some moons, can sustain convective ice flows, tectonic fractures, atmospheric chemistry, and possibly a subsurface ocean at a distance of 40 astronomical units from the Sun, then the Kuiper Belt is not the dead zone that earlier generations of scientists assumed. It is a region where planetary processes persist under conditions that seem impossible by inner solar system standards. 3.5 years after Pluto, New Horizons delivered its second revelation. On the 1st of January 2019, the spacecraft flew past a small Kuiper Belt object, designated 486958, Arrokoth, previously nicknamed Ultima Thule. Arrokoth orbits in the cold classical belt at approximately 44 astronomical units from the Sun. It is roughly 36 kilometers long, composed of 2 flattened lobes connected at a narrow neck. The shape, often described as resembling a snowman or a flattened peanut, was the first contact binary ever observed at close range. Arrokoth was everything Pluto was not, and that was precisely the point. Where Pluto is large enough to drive internal activity, Arrokoth is small enough to be completely passive. Where Pluto has been resurfaced and modified, Arrokoth's surface preserves conditions from the era of its formation. Where Pluto is a world with geology, Arrokoth is a fossil with a shape. The images confirmed what the formation models had predicted about Arrokoth's gentle assembly, but they also revealed details that no model had anticipated. The most striking feature was the flatness of the 2 lobes. Neither lobe is spherical, both are distinctly flattened, resembling thick pancakes more than snowballs. The larger lobe has been compared to a hamburger patty in profile. The smaller lobe looks like a dented walnut. This flattening was unexpected. Gravitational collapse models had predicted rounder shapes. The flattening suggests either that the lobes were shaped by rotation during their formation, or that subsequent processes, possibly sublimation of volatile ices from the surface over millions of years, gradually reshaped them after they merged. The surface itself offered another puzzle. At the resolution New Horizons achieved, Arrokoth showed almost no small craters. On most solar system bodies, small impacts vastly outnumber large ones, peppering surfaces with tiny pits at every scale. Arrokoth's surface was eerily smooth at small scales, suggesting either that the Kuiper Belt contains far fewer small impactors than models predicted, or that some process has erased the smallest craters over time. Either explanation carries significant implications for understanding the size distribution of Kuiper Belt objects and the collision environment of the cold classical belt. The overall impression was of an object that was assembled gently and then left alone for over 4 years untouched, unmodified, frozen exactly as it was at the moment of its creation. No violent history, no thermal processing, no gravitational disturbance. Just a small 2-lobed body drifting through the cold classical belt in a state of preservation that borders on the uncanny. For planetary scientists studying how the solar system formed, Arrokoth was an extraordinary find. It provided the first direct observational confirmation that planetesimals in the outer solar system formed through gravitational collapse rather than through gradual accretion via binary collisions. The implications extend far beyond the Kuiper Belt. If streaming instability and gravitational collapse are the dominant mechanisms for forming small bodies in the outer disk, the same processes may have operated throughout the solar system, shaping the initial building blocks that eventually assembled into the planets themselves. Arrokoth also revealed something about conditions in the cold classical belt that no telescope on Earth could measure. Its surface composition, its color uniformity, and its structural integrity all indicated that this region of space is astonishingly calm. The collision rate among objects in the cold classical belt is extremely low. Objects there are separated by such vast distances and move at such low relative velocities that violent impacts are rare. This is why delicate structures like contact binaries can survive for billions of years without being shattered. The cold classical belt is a cosmic deep freeze, preserving its contents with a fidelity that no other region of the solar system can match. But New Horizons was not finished delivering surprises. As the spacecraft continued outward through the Kuiper Belt after the Arrokoth flyby, its onboard dust counter, the Venetia Burney Student Dust Counter, kept recording. This instrument, designed and built by students at the University of Colorado Boulder, measures the rate at which microscopic dust particles strike the spacecraft as it moves through space. Dust in the outer solar system comes primarily from collisions between larger Kuiper Belt objects and from particles kicked up when KBOs are struck by interstellar dust grains. By tracking dust levels, the instrument maps the density of material in the belt. The expectation was straightforward and based on decades of modelling. The main body of the Kuiper Belt, the region containing the highest concentration of known objects, occupies the zone between roughly 30 and 50 astronomical units. Beyond 50 AU, the known population of Kuiper Belt objects drops off sharply. Surveys from Earth detect fewer and fewer objects at greater distances. The models were clear. As New Horizons moved beyond approximately 50 astronomical units, the main Kuiper Belt should thin out. Dust production, which depends on the collision rate between objects, should decline in step with the declining population. The spacecraft should have been flying into emptier and emptier space, recording fewer and fewer dust impacts as it left the belt behind. This prediction mattered because it represented a fundamental assumption about the outer boundary of the Kuiper Belt. If the dust levels dropped as expected, it would confirm that the belt has a well-defined outer edge near 50 AU, consistent with models of how Neptune's migration sculpted the region. The spacecraft would be crossing from populated space into genuinely empty space, transitioning from the Kuiper Belt into the vast void between the belt and the hypothetical Oort cloud. Instead, the dust counter detected higher levels of dust than models predicted. Between 45 and 55 astronomical units from the Sun, the readings remained elevated, suggesting a higher density of colliding objects in that region than the known population could account for. The signal did not fade as expected. It persisted. Something was producing dust out there, in a region where the models said almost nothing should exist. The data, published in the Astrophysical Journal Letters in early 2024, hinted at two possible explanations. Either the main Kuiper Belt extends much farther outward than current models estimate, meaning the population of icy bodies does not drop off near 50 AU, but instead continues at meaningful densities well beyond that boundary. Or a second, previously unknown population of icy bodies exists beyond the classical belt, a separate outer ring or extended debris field, producing its own dust through mutual collisions. Both explanations carry profound implications. An extended belt means the solar system's outer structure is larger than thought. A second belt means the solar system's outer structure is more complex than thought. Neither scenario was anticipated by the standard models that had guided Kuiper Belt science for decades. Alan Stern, the principal investigator of New Horizons, described the finding as potentially the first time any spacecraft had discovered a new population of bodies in the solar system. The statement carried appropriate caution. Dust measurements alone cannot definitively distinguish between an extended belt and a separate outer population. The dust grains themselves carry no return address. They arrive as impacts on the detector, registering as counts and particle sizes, without revealing whether they originated from a known population orbiting slightly farther out than expected, or from an entirely new class of objects in a previously uncharted zone. But the data represent a direct, in situ measurement of conditions in a region that has never been sampled before. No other spacecraft has operated instrumentation in this part of the outer solar system. New Horizons is the only probe currently collecting original data from within the Kuiper Belt, and its readings are telling scientists that the belt is not fading away as expected. Something is out there, producing dust, maintaining collision rates, and extending the structure of the outer solar system into regions that remain almost entirely unmapped. As of early 2026, New Horizons is in hibernation mode. deep in the outer Kuiper Belt, roughly 9.6 billion kilometers from Earth. A signal traveling at light speed takes over 8 hours to reach the spacecraft, and another 8 hours for the reply to return. The mission has been extended to continue gathering heliophysics and dust data until the spacecraft exits the Kuiper Belt, expected in 2028 or 2029. It has sufficient power and propellant to remain operational into the 2040s at distances exceeding 100 astronomical units from the Sun. No suitable target for a third close flyby has yet been identified, despite years of searching with the Subaru telescope in Hawaii. The Kuiper Belt is so sparsely populated and its objects so faint that even knowing New Horizons' precise trajectory, finding a reachable target requires extraordinary luck and painstaking observation. While New Horizons continues its quiet outward journey, telescopic discoveries from Earth have continued to reshape understanding of the belt. In May of 2026, a team of Japanese astronomers led by Ko Arimatsu of the National Astronomical Observatory of Japan announced the detection of a thin atmosphere around a Kuiper Belt object, designated 612533, also known by its provisional designation 2002 XV93. The object is a Plutino, roughly 500 kilometers in diameter, orbiting at about 40 astronomical units from the Sun. During a rare stellar occultation observed from multiple sites in Japan in January of 2024, the team detected a gradual dimming and brightening of the background star's light as the object passed in front of it. This smooth light curve, rather than the sharp cutoff expected for an airless body, indicated the presence of a thin gaseous envelope surrounding the object. The finding, published in Nature Astronomy, was startling. The atmosphere is estimated to be 5 to 10 million times thinner than Earth's. Likely composed of methane, nitrogen, or carbon monoxide, it should not exist by conventional expectations. An object this small, with gravity this weak, orbiting this far from any heat source, was assumed to be entirely airless. Pluto was the only trans-Neptunian object previously confirmed to possess an atmosphere, and Pluto is nearly 5 times larger. Even the larger dwarf planets, Eris, Makemake, and Haumea, show no confirmed atmospheric detections, though Makemake has shown hints. 2 hypotheses emerge to explain the observation. One proposes cryovolcanic activity, the eruption of subsurface volatile ices driven by residual internal heat, releasing gas that temporarily surrounds the object. The other suggests a recent impact by another Kuiper Belt body, which could have excavated subsurface material and released trapped gas into the tenuous gravitational grip of the object. Adding to the mystery, earlier observations by the James Webb Space Telescope had failed to detect the usual volatile ices, methane, nitrogen, or carbon monoxide, on the object's surface. If the surface lacks these materials, the gas composing the atmosphere must be sourced from beneath the surface, supporting either the cryovolcanic or impact hypothesis. Scott Shepard of the Carnegie Institution for Science, commenting on the discovery, noted that it demonstrates the Kuiper Belt is not a cold, dead place, but rather a region teeming with activity and harboring many of the building blocks for complex chemistry. The finding suggests that atmosphere-generating processes may be more common on small Kuiper Belt objects than previously believed, and that future occultation campaigns may reveal similar thin envelopes around other bodies in the belt. This single detection does not rewrite atmospheric science on its own. It is a candidate finding that requires confirmation through additional observations, but it fits a pattern that has been building for years, a pattern in which every new measurement of the Kuiper Belt reveals more complexity, more activity, and more surprises than models predicted. The next major leap in Kuiper Belt science is already underway, the Vera C. Rubin Observatory, located on Cerro Pachón in Chile, began its decade-long legacy survey of space and time with the largest digital camera ever built for astronomy. The survey is expected to discover approximately 35,000 new Kuiper Belt objects, increasing the known population by nearly a factor of 10. Most of these discoveries will come in the first year or two of data collection. The implications of this data flood are profound. With a tenfold increase in known objects, astronomers will be able to map the orbital distribution of the Kuiper Belt with far greater precision than current surveys allow. They will be able to test whether the orbital clustering that motivates the Planet 9 hypothesis is real or an artifact of incomplete sampling. They will detect smaller and fainter objects, filling in the size distribution and revealing whether the belt's population follows theoretical predictions or deviates in unexpected ways. They will identify new resonant populations, new dynamical families, and potentially new classes of objects that have no current analogue in the catalogue. The Rubin Observatory will also support New Horizons directly. A proposed deep drilling microsurvey aligned with the spacecraft's trajectory aims to discover Kuiper Belt objects close enough to New Horizons' flight path to be observed by the spacecraft's long-range camera at relatively close range. Even without a targeted flyby, imaging a Kuiper Belt object from a distance of 1 astronomical unit or less would provide data unobtainable from Earth, including information about surface properties, shapes, and rotation states at solar phase angles impossible to achieve from telescopes near the Sun. The convergence of New Horizons in situ measurements, the Rubin Observatory's survey data, the James Webb Space Telescope's spectroscopic capabilities, and ongoing stellar occultation campaigns from the ground is creating a moment in Kuiper Belt science that researchers describe not as incremental progress, but as a revolution. The belt is transitioning from a dimly perceived outer boundary into a fully characterized structural zone of the solar system, with its own internal architecture, its own population dynamics, and its own ongoing geological and chemical processes. Every new finding reinforces the same conclusion. The Kuiper Belt is not what anyone expected it to be. It is not a barren scattering of inert ice balls drifting through empty space. It is a complex, structured, and in some cases active region that preserves the earliest records of planetary formation, while simultaneously hosting processes that continue to operate today. Its objects carry atmospheres that should not exist, maintain shapes that record events from 4.5 billion years ago, and produce dust that hints at unseen populations stretching into unexplored space. But there is a dimension of the Kuiper Belt that no instrument can fully convey. The data reveal what is out there. The numbers quantify how far away it is. The images show what surfaces look like under the feeble glow of a sun reduced to a bright point. What none of these measurements can fully communicate is what it means to exist in that environment. Not as a data point on a chart, but as a physical reality. The cold, the dark, the distance, the silence, the overwhelming, annihilating emptiness between objects in a region so vast that even a spacecraft traveling at 14 kilometers per second needed years to cross it. That physical reality is where the true weight of the Kuiper Belt settles in, because the numbers that describe it are not abstractions. They describe a real place, a place that is part of the same solar system where you are sitting right now, connected to your world by the same gravity, the same sun, the same formation event 4.5 billion years ago, and yet the conditions there are so alien, so remote, and so hostile to every human instinct about warmth, light, and proximity that confronting them honestly forces a reckoning with the true nature of the cosmic neighborhood we call home. That reckoning begins with temperature, extends through darkness, scales through distance, and ends somewhere no map can reach. Begin with the cold, -230 degrees Celsius. That is the approximate surface temperature of a typical Kuiper Belt object. The number looks clinical on a page, just another figure in a textbook margin. But what it represents physically is something no human being has ever experienced, and no human body could survive for even a fraction of a second. At -230 degrees, every familiar substance on Earth transforms into something unrecognizable. Water is not merely frozen. It is locked into a crystalline state so rigid it behaves like granite. Steel becomes brittle enough to shatter on impact. Rubber crumbles into powder. The nitrogen that makes up most of the air you breathe freezes into a translucent solid. Carbon dioxide, the gas you exhale with every breath, becomes a rock-hard frost. Methane, the gas that heats your stove, turns into a pale crystalline ice. At this temperature, chemistry nearly stops. Molecular motion slows to the faintest vibration. Chemical reactions that proceed readily at room temperature become impossibly sluggish, requiring millions of years to accomplish what a few seconds would achieve on Earth. The biological processes that sustain every living organism, enzyme activity, cellular respiration, DNA replication, cease entirely. Life as we understand it is not merely difficult at these temperatures, it is thermodynamically impossible. This cold is not a temporary condition, it is permanent. The Kuiper Belt has existed at these temperatures for over 4.5 billion years, since the solar nebula cooled and the sun ignited. Nothing in that region has ever been warm by any standard a human being would recognize. The sunlight, reaching 40 astronomical units from the sun, carries roughly 1/1600th the intensity it delivers at Earth. At 50 astronomical units, it drops to 1/2500th. These are not dim conditions. These are conditions where the sun itself, the nuclear furnace that drives all life and climate on Earth, has been reduced to a faint point of light that would not cast a readable shadow on the surface beneath your feet. Imagine standing on the surface of a Kuiper Belt object. You look up. The sky is black, not the black of a cloudy night or a moonless evening, but the absolute black of a vacuum that extends unbroken in every direction. Stars fill the sky in numbers far exceeding what any earthbound observer has ever witnessed, because there is no atmosphere to scatter light, no light pollution, no blue sky to wash them out. The Milky Way blazes across the heavens with a clarity that would be breathtaking if the circumstances were not so profoundly isolating. And there, among the stars, is the sun. You can find it easily because it is brighter than anything else in the sky. But it is not a disk, it is a point. A brilliant, sharp, unwavering point of light, indistinguishable in apparent size from the brighter stars surrounding it. At 40 astronomical units, the sun's angular diameter has shrunk to about 48 arcseconds, less than 1/40th the apparent width it presents from Earth. Your eye cannot resolve it as a disk. The object that dominates Earth's sky, that heats your skin, that drives weather systems and ocean currents, and the water cycle and photosynthesis, and the entire chain of energy that supports every ecosystem on the planet, has been reduced to a star among stars. Brighter than the others, yes, but no longer the commanding presence that defines day and night, warmth and cold, life and death. Out here, it is just another light in the dark. The psychological weight of this transformation is difficult to overstate. Human beings evolved under a sun that fills roughly half a degree of sky, that warms exposed skin within seconds, that marks the passage of every day with a visible arc from horizon to horizon. Our circadian rhythms, our agricultural calendars, our religions, our art, our architecture, our very concept of time are built around the daily reality of a nearby, powerful star. The sun is not merely an astronomical object to human consciousness. It is the anchor of lived experience, the reference point against which everything else is measured. In the Kuiper Belt, that anchor is gone, not destroyed, not absent, just diminished to the point of irrelevance. The sun still exerts gravity that holds every Kuiper Belt object in orbit. It still emits photons that eventually reach these distant surfaces, but its warmth, its light, its visceral presence as a source of energy and orientation, all of this has dwindled into something that cannot sustain human perception of normalcy. You are still in the solar system. You are still orbiting the same star, but the star no longer feels like yours. Now extend your awareness beyond the cold and the dark to the distance itself. When New Horizons flew past Pluto in 2015, its confirmation signal, travelling at the speed of light, needed over 4 hours to cross the 32 astronomical units back to Earth. By 2026, with the spacecraft beyond 64 astronomical units from Earth, that one-way communication time has stretched to over 8.5 hours. A simple command sent from Mission Control will not reach the spacecraft until the following work shift. The confirmation that the command was received and executed will not arrive until the shift after that. This is not a metaphor for isolation. It is the physical mechanics of isolation expressed in the most fundamental unit available, the speed of light. At Kuiper Belt distances, the universe's absolute speed limit becomes a prison wall. No message, no signal, no beam of light can travel fast enough to create anything resembling real-time interaction between this region and the inner solar system. Communication becomes a series of monologues separated by hours of silence, each party speaking into a void and waiting half a day for a reply. For a spacecraft, this delay is an engineering challenge, solvable with autonomous software and careful planning. For a human mind attempting to comprehend what these distances mean, the delay is something closer to vertigo. We are accustomed to a solar system that feels connected. We watch live feeds from Mars rovers delayed by only minutes. We see images from Jupiter's moons returned within hours. The inner solar system, for all its vastness, still operates within a communicative horizon that feels manageable. The Kuiper Belt demolishes that illusion. Out here, the solar system is too large for conversation, and the distances between objects within the belt are even more disorienting than the distance from the belt to Earth. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers. It may contain billions of smaller ones. Yet the volume of space these objects occupy is so staggeringly immense that the average distance between any two large Kuiper Belt objects is measured in tens of millions of kilometers. New horizons had to be aimed with extraordinary precision years in advance to pass within 3,500 kilometers of Arrokoth, a target roughly 36 kilometers long, embedded in a region where the nearest comparable object might be 50 million kilometers away. The spacecraft threaded a needle across billions of miles of empty space to reach a single tiny body drifting in a void so vast that missing it by even a fraction of a degree would have sent the probe sailing through nothingness for years, without encountering anything at all. This sparsity is one of the Kuiper Belt's most important and most underappreciated physical characteristics. Diagrams compress the belt into a dense band of dots for the sake of legibility. The visual impression is of a crowded ring, thick with objects, busy with material. The reality is the opposite. The Kuiper Belt is overwhelmingly empty. Its objects are separated by gulfs so wide that if you stood on one Kuiper Belt object and looked in every direction with the most powerful telescope imaginable, you would not see another one. There would be nothing to see, just black sky, faint stars, and the distant speck of the sun. Compare this to the inner solar system, where planets are visible to the naked eye from each other's surfaces. Standing on Earth, you can see Venus, Mars, Jupiter and Saturn without a telescope. The moon dominates the night sky. The sun fills the day. The inner solar system is populated enough, close enough, and bright enough that celestial neighbours are part of everyday human experience. Ancient civilizations tracked planetary motions with their unaided eyes and built entire cosmological systems around what they observed. In the Kuiper Belt, that entire framework vanishes. There are no naked eye neighbours. There is no bright wandering star to track across the seasons. There is no nearby moon to light the landscape. There is only the object beneath you, and an emptiness so complete that the concept of a neighbourhood becomes meaningless. Each Kuiper Belt object is an island, separated from every other island by distances that would take centuries to cross at any achievable speed. This is the reality that textbook diagrams conceal. The solar system does not transition gradually from busy to empty. As you move outward, it crosses a threshold. Inside Neptune's orbit, the solar system is a structured, populated environment where gravitational interactions are frequent, where objects influence each other across relatively short distances, where energy from the sun drives weather and geology and chemistry on every world. Beyond Neptune, that structure begins to dissolve. The objects are still there, but the spaces between them have expanded to the point where each one exists in functional isolation. The Kuiper Belt is not a continuation of the inner solar system's pattern. It is the beginning of something fundamentally different, and the Kuiper Belt is not even the end of the story. Beyond the main belt and the scattered disk lies a far vaster structure that has never been directly observed. The Oort cloud, hypothesized by Dutch astronomer Jan Oort in 1950, is a theoretical shell of icy bodies surrounding the entire solar system at distances ranging from roughly 2,000 to 100,000 astronomical units from the Sun. If the Kuiper Belt is the porch of the solar system, the Oort cloud is the property line, a boundary so distant that it stretches a significant fraction of the way to the nearest neighbouring star. The Oort cloud has never been seen. No telescope has ever resolved an individual object within it. Its existence is inferred entirely from the orbits of long-period comets, which arrive from random directions with orbital periods stretching into millions of years. These comets must originate from a vast, roughly spherical reservoir at extreme distances, and the Oort cloud is the name given to that reservoir. Estimates of its population range from several hundred billion to a few trillion icy objects, though most are thought to be small, perhaps a few kilometers across. If the Oort cloud exists as modelled, the Sun's gravitational domain extends more than 1.5 light-years from its centre. The nearest star to the Sun, Proxima Centauri, lies just over 4 light-years away. The Oort cloud, at its outer edge, reaches more than a third of the way to the nearest neighbouring star system. The solar system, properly defined to include all gravitationally bound material, is not the compact arrangement of planets and asteroids that fits on a classroom poster. It is a structure measured in light-years, a sparse halo of frozen debris extending so far from the Sun that the Sun's own gravity is barely sufficient to hold it together. A passing star or a gravitational perturbation from the Milky Way's disk can dislodge Oort cloud objects from their orbits, sending them tumbling inward on million-year journeys toward the inner solar system or outward into interstellar space forever. The Kuiper Belt sits at the innermost margin of this vast outer domain. It is the last structured region, the last place where distinct dynamical populations and orbital patterns can be mapped and studied. Beyond it, the scattered disk thins into a diffuse haze, and beyond that, the Oort cloud stretches into theoretical territory that may never be directly observable with current or near-future technology. This layered architecture reveals something deeply unsettling about the solar system's true nature. The warm, bright, geologically active zone that humans know and study, the zone containing Mercury and Venus and Earth and Mars and Jupiter and Saturn and Uranus and Neptune, occupies a vanishingly small fraction of the Sun's total domain. If you could somehow shrink the solar system so that the Oort cloud's outer boundary fit inside a sphere the size of a football stadium, the entire planetary system from Mercury to Neptune would occupy a volume no larger than a tennis ball sitting on the 50-yard line. Consider what that means through the lens of the only object humans have ever sent into this outer wilderness. New Horizons was launched in 2006 aboard an Atlas V rocket. It left Earth faster than any spacecraft before it, travelling at roughly 16 kilometers per second. It crossed the orbit of the Moon in just 9 hours. It passed Mars's orbit in less than 3 months. It reached Jupiter in 13 months and used the giant planet's gravity to slingshot itself even faster toward the outer solar system. After 9.5 years of flight, it arrived at Pluto. After 13 years, it passed Arrokoth. As of 2026, it has been travelling for 20 years at speeds exceeding 14 kilometers per second, and it has reached 64 astronomical units from the Sun. It is expected to exit the Kuiper Belt in 2028 or 2029, roughly 22 to 23 years after launch, and yet, at that point, it will have crossed only the innermost fringe of the Sun's outer domain. The Oort cloud begins at roughly 2,000 astronomical units. At its current speed, New Horizons will not reach the inner edge of the Oort cloud for roughly another 700 years. It will not reach the outer edge for approximately 30,000 years. The fastest spacecraft ever launched from Earth will spend 7 centuries just approaching the threshold of the Sun's true boundary and 300 centuries crossing it. That is the scale of what lies beyond the Kuiper Belt. And the Kuiper Belt itself, the The structured, populated, scientifically accessible part of the outer solar system is merely the doorstep. The familiar solar system is not the solar system. It is the innermost core of the solar system, surrounded by an ocean of cold, dark, empty space extending outward for trillions of miles in every direction. And the Kuiper Belt is where the transition begins. It is the threshold, the boundary zone where the orderly, planet-filled inner system gives way to the sparse, frozen, unimaginably vast outer wilderness that constitutes the true bulk of the Sun's gravitational kingdom. This is what the title of this story means. The terrifying reality of the Kuiper Belt is not that it contains some single monstrous object or some specific existential threat hurtling toward Earth. The terror is structural. It is the terror of scale, of cold, of emptiness, of realizing that the solar system you thought you understood was a small, warm, well-lit room embedded in a mansion so large you cannot see its walls. Think about what this means for the human picture of cosmic home. Every civilization that has ever looked up at the night sky and drawn a map of the heavens was mapping the inner room. The Greeks saw the planets and called them wandering stars. Copernicus placed the sun at the center and the planets in orbit around it. Kepler refined the orbits into ellipses. Newton explained the gravity that holds them in place. 4 centuries of telescopic astronomy catalogued moons, rings, asteroids and atmospheres. Spacecraft visited every planet. The solar system felt known, it felt mapped, it felt, in some meaningful sense, finished. The Kuiper Belt ends that feeling. It reveals that the mapped portion of the solar system accounts for a tiny fraction of the whole. The rest is frontier, wilderness, unexplored and in many cases unexplorable with current technology. And the frontier is not a narrow borderland between the known and the unknown. It is the dominant reality. The wilderness is larger than the settlement by orders of magnitude. Humans have not explored most of their own solar system. They have explored a small, bright core and mistaken it for the entire structure. The emotional weight of this realization lands differently than most astronomical facts. Learning that the universe contains 2 trillion galaxies is staggering, but it involves distances so abstract that the mind simply acknowledges the number without fully processing it. The Kuiper Belt is different. It is close. It is part of the same system where Earth orbits. It is connected to the same sun that rises over your horizon every morning, and yet the conditions there are so hostile, so remote, and so alien that they might as well belong to another universe entirely. This is the dissonance at the heart of the story. The Kuiper Belt is ours. It belongs to the same star, formed from the same cloud of gas and dust, obeys the same laws of physics, contains objects made from the same elemental ingredients as the ground beneath your feet, and yet it is a place where the sun is a distant point, where temperatures have not risen above -200 degrees in 4.5 billion years, where the nearest neighbouring object is farther away than most people can comprehend, and where silence and darkness are not conditions of nighttime but the permanent, unbroken state of existence. Pluto orbits in this region. Pluto, the world that schoolchildren learned was the last planet, the world that received a spacecraft visit and turned out to have glaciers and mountains and an atmosphere and possibly a hidden ocean, exists in a place where the sun provides less warmth than a birthday candle viewed from across a football stadium. The mountains of water ice on Pluto are hard as steel. The nitrogen glaciers flow at rates measurable only over geological time. The atmosphere, such as it is, would register as a near-perfect vacuum by any standard used on Earth. And Pluto is one of the warmer, more active, more geologically interesting objects in the belt. Most Kuiper Belt objects receive even less sunlight, have even lower temperatures, and show even fewer signs of activity. They are frozen completely, sealed in a state of suspended animation that has persisted since before life appeared on Earth. Arrokoth, the snowman-shaped fossil that New Horizons visited in 2019, has not changed in any meaningful way since its formation. Its 2 lobes merged gently over 4 billion years ago, and nothing has happened to it since. No impacts large enough to reshape it. No thermal cycles to alter its surface. No gravitational interactions to disturb its orbit. No. It drifts through the cold classical belt in a state of preservation, so complete that studying it is like reading a letter written by the solar system to its future self, a message composed at the moment of birth and delivered unchanged across the full span of cosmic time. The Kuiper Belt preserves. That is one of its defining characteristics. The cold prevents sublimation, the distance prevents solar heating, the isolation prevents collisions. Everything placed in this region during the solar system's formation remains there, frozen, dark, undisturbed, accumulating nothing but a slow patina of cosmic ray damage and a thin coating of tholin chemistry on its surface. The belt is a museum with no visitors, no curators, and no lights, holding exhibits that predate every living thing that has ever existed. And yet this museum is not merely a relic. It is a place that still operates, still produces comets that seed the inner solar system with ancient ice, still generates dust that fills the outer reaches with a faint haze of microscopic particles, still harbours objects that maintain thin atmospheres against all expectations. It is a frontier that is simultaneously ancient and active, dead and alive, finished and barely explored. The Vera Rubin Observatory will soon multiply the known population of Kuiper Belt objects by a factor of 10. New Horizons will continue collecting dust and plasma data as it exits the belt in 2028 or 2029. The James Webb Space Telescope will measure surface compositions of distant Kuiper Belt objects with spectroscopic precision that was impossible a decade ago. Stellar occultation campaigns will probe for atmospheres, rings and moons around objects too ball-stained and too distant for direct imaging. Each of these efforts will add detail to the picture. Each will reveal new surprises, but no survey, no spacecraft, no telescope will change the fundamental reality that the Kuiper Belt forces you to confront. It is the place where the solar system stops feeling like a neighborhood and starts feeling like an abyss. It is the zone where distance overwhelms proximity, where cold overwhelms warmth, where emptiness overwhelms structure, and where the human mind's ability to project familiarity onto the cosmos finally reaches its limit. The 8 planets orbit in a warm, bright, compact region that human civilization has studied for millennia. Beyond them lies a frozen outer world that dwarfs the planetary zone in every physical dimension, volume, radial extent, population count, and duration of preservation. The Kuiper Belt is not an afterthought appended to the edge of the solar system. It is a fundamental structural zone that reveals the true character of the Sun's domain, a domain that is overwhelmingly cold, overwhelmingly dark, overwhelmingly empty, and overwhelmingly indifferent to the existence of the small, warm world where human beings happen to live. The solar system you carry in your imagination, the one with the bright sun and the colourful planets and the rings of Saturn catching the light, is real. It exists. But it is a small, sheltered clearing in the middle of a vast and frozen wilderness. And the Kuiper Belt is where that wilderness begins. Not at the edge of the sun's gravitational reach, not at the theoretical boundary of the Oort cloud. Right there, just past Neptune, barely beyond the last familiar landmark, the solar system transforms into something colder, stranger, and less human than most people have ever been asked to imagine. That is the terrifying reality. Not a single object, not a single threat, but the simple, confirmed, measured, observed fact that the solar system we think we know already gives way, far sooner than anyone expects, to a frontier of cold and isolation so vast that it makes the entire familiar planetary system look like a campfire burning in the middle of an endless, frozen night.